So, today's lecture, it feels weird calling it a lecture given that it's a stream, but today's amount of information is going to be on kinematics. So kinematics essentially is the study of motion. And particularly, we're going to look at rectilinear motion for the minute. Okay, not tough shit, but like, yeah, go grab a drink, go do the thing. I've been live for 20 minutes. If you're not ready now, you're never going to be ready. So get on it. We're going to start. So rectilinear is basically just a fancy way of saying like straight line motion. Or as much as like in contrast to later down the line when we start looking at circular motion and things moving in a rotational frame. Why recti and rectilinear? I actually don't know. Have a look at the etymology. Comes from straight line, basically. The recti means straight and the linear means line. That's it. That's the that's the definition. Yeah, so it's essentially just in contrast to the circular motion, we will see later, which I think is about 5 or 6 streams away from now. So by line they mean curve, yeah. So linear as opposed to non-linear and rectangular as opposed to circular, I think is the like contrast. Banana, I was trying really hard to stay away from the word rectum. I was like, we've just started. But yeah, basically like rectangle, that side of thing, like think along that way rather than circular. So it's all, we can break it down into, we can break it down into sort of vertical and horizontal, or we can describe it using Cartesian coordinates. So it's all sort of angular. Then the kinematics is motion. So typically, going back to sort of a conversation that we had last time, we have, for a given point, in order to yes, oh, come on, describe it with vectors. It would help if I could spell.
Was good maths needs. I'm done with Waku Ubang.
Hello. Thank you, Memeg. Sorry, I had to like pass that through my brain a little bit. Much appreciated. Yeah, but so for a given point, in order to describe it with vectors, we need a frame of reference. So remember how last time we had like distance versus displacement and velocity. So displacement is like distance away from a point, or distance as with respect to a given origin or like a given start point. Velocity then is the speed with respect to a distance. So it's the vector versions of things. So these are vectors, and then these are the scalars. And then again, acceleration is kind of like, acceleration is a vector because it has an orientation, like gravity goes downwards, but we also kind of say the magnitude of acceleration when we mean the scalar version. So typically if I say displacement or velocity, they are the vector quantities that we're talking about, and we're going to lean more that way. So when we talk about things with Cartesian coordinates, so typically we break things down into their horizontal and then vertical components. So horizontal, meaning like x-axis, or sometimes if we're not doing like axes yet, I'll just do like a little arrow. I mean horizontal, and vertical, y or z, depending on who you are, axis, components. And this will come in handy later down the line when we start doing projectile motion, because we talk about distance traveled in the vertical and distance traveled in the horizontal. For the minute, let's just stick with sort of unidirectional motion. So in 1D, so there's a really good reason why we use displacement rather than distance, which hopefully this example will demonstrate. So if we have a point A, and we have point B, and then somewhere between them we have a point C. Okay, and I say I walk from A to B and then back to C. So that's my total travel time. And let's say the distance between A and C is like 50 meters, and the distance between C and B is 25. Oh, that just is the end of the page. That's why that's not working. Then we have that the total distance So the total distance that I walk is I have to go from A to C, then C to B, then B to C. So AC plus B plus B, which is 50 plus 25 plus 25. That's a total distance of 100 meters. Okay. In contrast, if I walk A, B, C, and I want my total displacement, and I'm going to say that that is the positive direction. Oops, sorry. I'm going to say that that way is the positive direction. Then it would actually be the distance AC plus, again, CB and then BC. But now, this is still 50 because I've said that way is, sorry, my image is flipped. So that way is still positive. So A to C is positive 50 meters. C to B is positive 25. Then B to C is then negative because I'm going back on myself. That's now minus 25. So my total velocity, total displacement is 50 meters. And I can leave it at that for the minute because I'm working in one direction. So I've just said positive. So if it's positive, it's going that way to the right. And if it's negative, it's going to the left. So the distance traveled is actually much further than the total displacement, which makes sense when you think about if I go somewhere and then come back, I've walked twice the distance between the two, but my net travel is 0 because I'm back where I started. So this is why it's really important to kind of make sure that we're saying the right ones depending on what we mean. Did one of the mods get rid of that ad break, or is it about to appear, by the way? I'll try and make sure I'm quiet while it's on. I used to have a thing on OBS. It has been snoozed. Excellent. I used to have a thing that let me control ads, and that's just completely disappeared from OBS in its entirety. There are buttons that let me add ads. At least you snoozed it. Yeah, that doesn't just work for you, Tech. I think that snoozes it for everyone. Fantastic. We'll see what happens. I'll make sure I pause. Don't worry. Yeah, so that's our total displacement. If we have a walking speed, no, the other way around. So if the trip takes 5 minutes, we can then work out our speed and our total velocity. Again, so they relate to our total displacement and our total distance. The other way around. So total speed, or net speed, is distance over time. So it's 100 meters over 5 minutes in seconds. So we do 5 times 60, which is 300 seconds. So that gives us a speed of 0.3 recurring meters per second. So that dot over it means recurring. So 0.33 if you want to be snazzy. But in contrast, our total velocity, or our average velocity, because maybe we sped up and slowed down, but for the minute we're assuming constant, is our displacement. So it has the same relationship. Hello, welcome in. You've been following me since March. Fun fact. Welcome. Yeah, so it's the same relationship. Speed is distance over time. Velocity is displacement over time. So our velocity is now 50 over 300. So that is 0.16 recurring meters per second. There's some slow walking. Yeah, okay, so these numbers are made up by me and not sanity checked. We're meandering. We're going on a stroll. I think for context, average walking speed is like 1.2 meters per second. So this is really, really, yeah. We're taking our time. We're taking our time. Maybe it's like distance in a wheelbarrow race or something. No, people go faster in those. Bad wheelbarrow race. Or egg and spoon or something. Like something where people slow down. It's like when you have 60 apples. Yeah. So the velocity is lower than the speed here. Which might feel unintuitive, but if you think about it, the only thing we really care about is our start and end time, because we're assuming constant speed. So the distance that we travel is further, but in terms of, my start and my end goal, if I don't see how you got there, all I know is it took you 5 minutes to go 50 meters, regardless of the fact that you actually went an extra 25 and then came back. Which kind of comes back to this whole, the shortest, I'm going to do a little mathsy segue. Mathsy aside. So the shortest distance between any two points is the straight line connecting them. Okay, and this is actually an axiom, meaning it's so, oh geez, stop. Sorry, my pen glitched out. Meaning it's so fundamental that it's taken as truth. It doesn't require any other things sort of to prove it. We kind of take it as gospel. I think it's one of Euclid's 5 axioms. What is it? Ooh, stop. Am I lying? How long has it been since I've done geography? Euclidean geometry. Axioms. Straight line between one point and another, produce a finite extent line. Straight lines can be extended. Circles can be described by a center and a distance. Right angles are equal. Two straight lines are parallel. Okay, no, so it's not. Although it does then define a straight line. So get rid of that bit. But it is essentially fundamental in as much as, like, if you think of 2 points here and here, A and B, if I were to measure that length versus lying a bit of tape down like that, and then sort of lie a string around it and then stretch that out straighter, obviously that wiggly line that I've drawn is going to be much longer, and it's not possible to get one shorter. Still, they can be proven with calculus variation concepts, consider the integral of every possible curve and minimize. Yeah, so there are ways to prove it. I think I'm wrong in saying that it is an axiom. It is a fact, at the very least in Euclidean geometry. Distance between 2 points. Is a straight line always the distance between 2 points on scienceabc.com? No, it depends on the geometry. That's not helpful. Okay, this is essentially saying that spherical geometry exists. Yeah, in planar geometry, so on flat surfaces, the straight line is shortest distance. I think there's some fun thing that you can do to disprove the Earth being flat with this, if you really wanted to, just to go cause some chaos. But yeah, so straight lines are pretty cool. And that's why, in this instance, that the speed between the 2 points is sort of faster there. Ooh. So I'm a really visual person. I really like learning through sort of diagrams and kind of seeing concepts, which I think is why I like mechanics and applied math so much, is because it is fundamentally very visual. So the best way to kind of describe velocity and time for simple relationships, when things start getting really complicated, then maybe that's a plug it into a computer and plot it type deal. But for the minute, the best way to describe these sorts of things with constant velocity or constant acceleration is by drawing them. So we have our time graphs. Typically either as displacement time, graphs, or velocity time graphs. Okay, so these then are typically drawn, they can be drawn otherwise, sometimes it's nicer to do it this way, as your okay, I think I'm going to stop using that and just actually use the straight line tool. So we tend to draw time along the bottom, and let's do displacement first. F0 in the back, because we should always label our axes. It's very important. So basically what this is saying is, as time is progressing along the bottom, you're talking about your displacement, so your distance away from the origin. So if I were to kind of start walking at some rate I would get maybe something like this. Okay. And what's happening here is as time is progressing, I'm getting further away from my start point. So, and it's that gradient, that the sort of elevation of that line is constant. It's a straight line. So what this tells me is I have, so as time progresses, I move further away from the origin with constant rate. Okay, and that constant rate of change of displacement is exactly constant velocity. In contrast, I could be moving sort of in a downwards motion. So as time progresses, I move further closer to the origin, or things going downwards. And maybe that's negative velocity. So positive or negative just means that that line, that gradient is constant. Okay. What I might have instead is something like this, where let's pretend that was actually a straight line. So here, ooh, come back here. Nope, that one. So this is as time progresses, I'm unmoving. Or at the very least, I'm a constant distance away from things. I could, in theory, be walking in a giant circle around the origin, but that's typically far away from the examples that we see. Distance. So, 0 velocity. And then the other one that you might see maybe is something like this, which then is as time progresses, I'm moving with increasing velocity. Okay, so non-constant. So typically it won't be too complicated of a thing, but you might, basically, if you've got a straight line, there's constant velocity. If you've got a horizontal line, there's 0 velocity. And if you've got anything else, it's a non-constant velocity. So you can get all sorts of complicated things. Normally you don't see anything more complicated than maybe like parabolic. So a nice curve, maybe exponential if something's multiplying or growing really, really fast or spreading. But for our intents and purposes, these are the 3 sorts of things you'll see. And again, they can be moving downwards or they might be slowing down. But we'll get to those when they happen. So similarly, we have displacement, velocity time graphs. So as the gradient of a displacement time graph is velocity. Gradient of a velocity time graph is then acceleration. The velocity time graph, acceleration. Yeah, I've clocked that tag. Thank you. So now velocity time. And again, we have sort of constant. acceleration, we have 0 acceleration. And we might even get sort of decreasing. Well, that's technically increasing negatively. I'm going to write non-constant. Decreasing slash increasing. Yeah. So there are also, like, as they get closer to the origin, you can also move into sort of negative velocities, as I said, when you're working just in that one direction, that look a bit different. So here, for example, yeah. Let's do something like this. So V, E. And if our plot looks like this, at our 3 different times, and then let's call this point A, point B, and point C. This might be what I was looking at before, where I had my, well, technically it's lowercase now, and B, where I'm moving in a positive direction. So I've got, I actually have increasing velocity here, so let's change this to my X, because this is technically my displacement time graph, sorry. So here I'm moving from A upwards towards B, and then turning around and coming back towards C. And the lines are straight, so this is moving with constant velocity. So constant velocity here. So this section from A to B here will have some velocity V1, which is that gradient, and then this velocity will be V2. And in our example above, we assumed that it was constant speed, so we worked out what the speed was, which then gave us our velocity in the 2 directions. So we assumed that those gradients were like equal but opposite directions to each other. So yeah, velocity is like magnitude and direction, so size and direction. So typically the magnitude of the velocity is the speed. Hopefully that helps. So I want to do oh, I wrote constant velocity. Sorry. No. Don't apologize. Do not apologize. So that's constant speed. Yeah, please do call me out on things. Okay, so if we work under the assumption, heck, be nice. If we work under the assumption of constant acceleration, then constant acceleration means that the gradient of okay, so that means that in our gradient of our rate of change of velocity is constant if we've got constant acceleration, because acceleration is just rate of change of velocity, which means we're looking at straight line graphs in dt. graphs. Okay, remember gradient equals rate of change. And acceleration is the rate of change, so that dv dt, change with respect to time of velocity. So that gives us this wonderful graph, which I have drawn out many times in my life. So B, we've got some acceleration. It doesn't have to be that angle exactly, but like, let's go with it. Then I'm gonna take 2 times. Let's take this time here, 1, and some later time t2. Title is wrong. Oh, god damn it. I did have it. I did set it right at the beginning because people were mocking me for Mechanics mini-series. It's changed the category as well. Okay. Right. Let's hope nothing else breaks on us. Okay, so we got time t1 and t2. And I'm going to say, like, the time between these two, I'm just going to call that t. So that's our time of interest. Okay, so we have our starting point here. And we have our ending point there. So I'm going to call this initial velocity, so the velocity at time 1, where we start, I'm going to call it u. And I'm going to call this one v. Okay. I'm going to do that for a reason that will make sense. So let's label the points as well. Let's call them A and B. So at time 1, we are at A with velocity u. Thank you for the follow. Welcome in. And then at time t2, and I'm going to say that t2 is bigger than t1. We are at with velocity v. Okay. So we know that the gradient of a velocity time graph is the acceleration. So we can say that the acceleration equals gradient. And the gradient of a graph, in order to work it out for just a straight line graph, is rise over run, is how I always remember it. Run. There we go. So our rise is our vertical distance up. So that's our top point minus our bottom point. So here we have a value of v minus u. So that's v minus u. And our run is our later time minus our earlier time. So t2 minus t1, which is exactly that distance. Right, I've said t is the length of that line, which is mildly confusing because that's the same as the axis label, but don't worry about it. This is just convention. So that gives us our first equation. A equals v minus u over t, which is more commonly written if we rearrange this and multiply everything by t and then move over, we get v is plus at. Okay, so I've multiplied that by t, and then I've taken that u over to the other side and just written it this way. So that is our sort of first equation that we care about. So the other one that we can derive from like this picture is for displacement. So displacement with regards to a velocity time graph, if we go way, way, way back, I said that velocity was rate of change of displacement and acceleration was rate of change of velocity. So graphically, Sorry, I'm just having issues with my mouse. So remember, we have x dx dt equals v, and dv equals a. So the rate of change of x is v, and the rate of change of v a. In the same way, we have x is the integral of v t, and v is the integral of a. They're all just functions with respect to time. So we can integrate. So integration, in the same way that derivative, so of straight line graphs are gradients. Integrals, and this is true of other graphs as well, but for the minute, are area under the curve. So when we look at this picture up here, we can work out the area under the curve. So in particular, what I'm saying here is I want this, the value of this area here is going to be equal to our displacement. So in order to do that, we call displacement. So displacement S rather than X for reasons is area. So it's going to be that rectangular-y bit that I'm going to call 1 plus that triangle-y bit that I'm going to call 2. So looking up here again, our first rectangle, so we've got a height of u and a length t for our rectangle, and then the height of the triangle is v minus u again, base is t, half v minus u times t. And I'll write it out because saying maths is hard. So that rectangle bit is u times t, and then the triangular bit is the length is v minus u. The height is v minus u, the length is t. Thank you for hanging around. I love your username. Amazing. And I really appreciate it because I get, nervy about this stuff sometimes. Very cool. Yeah, I'd love to check out what other people are doing. So that's half of that. Okay, this is really awkward to look at. Thank you for the follow. Welcome in. Appreciate it. So remember how we said that we have v is u plus at. We're just going to substitute that in. So we get s is ut plus half u plus at minus u t. So the u's cancel. So we get s is ut plus a half a t squared. And that is our second equation. So in theory, those are all of the ones that you can get from this graph. But given that we've got 5 unknowns, we want a few more equations just to make it a bit easier, so that rather than having to substitute in and then multiply and manipulate the 2, let's just remember a few more equations. So let's look at 1 again. So we got v is plus at. I'm just going to square it. I'm going to v squared is u plus at times u plus a. And that gets me v is doing my crescent moons if you do it that way, but first outside, inside, last, multiply each of these things together. So doing the first one, you get u squared plus, and then we do u times at twice, so 2u at plus a squared t squared. Okay, The v squared and the u squared look alright. Let's leave them alone. Okay, then we've got 2uat plus a squared t squared. Well, that looks really similar to equation 2. So let's manipulate it. So let's take the 2a out, and then that gives us ut plus half at squared. Which is precisely the thing from equation 2. So equation 3 is v squared equals u squared plus 2as. I'm going to write all these out nicely, don't worry. Okay, so now we have equation 3 doesn't have a t in it, equation 2 doesn't have a v in it, and equation 1 doesn't have, where has it gone, an s in it. So let's try and get one without a u in it. No, without an a in it. Sorry. So finally, let's look at s is ut plus half at squared. Okay, what can we do here? Let's do s is t times plus half a, t even. Okay, we want to get rid of the a, so let's remember that we've got v is u plus at, so that gives v minus u over t. A, remember our rise over run equation, so that gives us s as t u plus half minus u t times t. S is t times, right, so we've got the u, the t's cancel here, plus half v minus half u. So u minus half u, we just get positive. So that gives s is u plus v over 2. And that is equation 4. Okay, so 4 equations, 5 unknowns. There's a whole linear algebra reason why this is great. But basically, for our intents and purposes, it means that I can draw this cool thing where if we write down our equations, we get v plus at. S is plus half a squared. Squared is squared plus 2as. Then finally, s is plus u times t over 2. Then I do, let's do this in an order that makes sense. S, T, A. Okay, so this one doesn't have an S, but does have all of those. The next one down, there's no V, so, but it does have the others. Next one, there's no time. There's not enough time. And then the final one has no acceleration. So they're not written in an order that is helpful for my graph, but this is really useful because. Sorry, I'm over the T. Basically what this means is if you have displacement, initial velocity, final velocity, acceleration, and time taken. Thank you for the follow, welcome in. Yeah, if you have 4 of these, actually no, if you have 3 of these and you want to find one of the others, you can do that. So any of these equations, because they don't use all 5, if I have no idea about displacement, but I have initial velocity, acceleration, and time taken, I can figure out the final velocity. So it reduces down the number of things you need to work out. And then we can use, you know, once we get 4, we can get the 5th one. But it means we only need 3 to find 1 rather than 4, which is just making it ever so slightly nicer. And how I've written it here, this S, U, V, A, T is why I called it the SUVAT equations. So I know that different people call them different things. This is like the PEDMAS, BODMAS, PEMDAS, BIDMAS, all of those things. They're all the same thing. I know that there is some argument with SUVAT as well, but I call them SUVAT. This is how I was taught them. They work pretty decently. So let's do an example. The main sort of SUVAT equations that you're going to see, the sort of problems that come up, Zubat, which is a Pokemon. Yeah. This week's Pokemon monster is Zubat. Deal with it. Why not? Yeah, the main time that this comes up at the very least is sort of projectiles or things in free fall. Basically anywhere where you have constant acceleration, you've got things like gravity playing. Most problems, I would say, are typically things involving gravity because that is a constant accelerational force, rather than a car where you're accelerating and decelerating. SUVAT is the physics ripoff. Yeah, basically. Confirmed. So yeah, let's keep going. So SUVAT equations are often used in things like projectiles, free fall, or other gravity-driven motion. So there might be some like initial, like if I'm throwing something, it's still a projectile because as soon as it's out of my hand, I have given it that initial velocity and then it's just constant. And in particular, gravity only works in the vertical. So with a projectile, where we know air resistance, air resistance is the bane of nice, simple kinematic equations, okay? It's no air resistance here. She doesn't go here. But if you do have just gravity, then you always have some sort of minus g acting downwards, and then don't like that arrow. Do it again. And then you always have like 0. So there's no forces that pull a projectile in a horizontal motion, which is why gravity getting rid of, air resistance getting rid of is so useful, because otherwise you have it slowing it down. Yeah, if it's non-constant, then you go back to this sort of needing to actually do some differentiation and figuring out what your rates of change are with respect to your variables, and we start doing some calculus. But for the minute, we're just gonna disregard that. So, projectiles. Which are nice, like, think throw a ball rather than like launch a spaceship. Things without their own internal motion or combustion going on. And I timed that beautifully because we are about to go into another ad break. Haha. Yeah, so that's what we're going to do next. And I have a physics, an exam style question, which what I wrote. So we'll see how absolutely absurd the values that I used are. So who knows? I think I tried to make it at the very least physical. I just don't know if it's rational in the same way that like 0.1 meters per second as a walking speed is like fine, just a bit weird. Okay, so some things to know about projectile motion. Typically, we're not talking as no internal combustion. Think more ball thrown than spaceship. Although, maybe later we do some Kepler's law. No spontaneous combustion, no like internal forces. There's nothing like propelling it beyond the initial velocity. All of this stuff breaks as soon as we have non-constant acceleration, basically. So you could do constant acceleration, I guess. But typically we have things that are going to fly from point A to point B. Something like this. There we go. Kind of like that. And from A, if I did like a little zoom in thing here, I would get, we have our vertical velocity, which, or vertical direction, which I think I'm going to call Y. And we have our horizontal direction, X, and we set our origin to our initial point. We might not, there might be a reason not to, but typically it's going to align with where we start. And that's going to get yeeted with some initial velocity, U, as we said. It has our initial velocity, and that's going to be at an angle theta to the horizontal. Okay, so things are thrown. Yeah. Things are yeeted with initial velocity U in direction theta at an angle, actually. To the horizontal. Again, we could describe it as an angle from Y. We're just choosing it to do it this way for the minute. They have no internal motion. It's as soon as it's going, it's going. We define gravity. So acceleration is working downwards. So acceleration is in the negative vertical direction, with A as minus G. The G is normally like 9.8, 9.81, 10 if you're a physicist, I guess. Relative acceleration, yeah. 9.8 ms to the minus 2, because we're being good. U, and actually let's put our meters per second. Yeah, so we can use SUVAT to figure out anywhere along this direction, okay? So anywhere along the path that the particle takes, we could do SUVAT. So we could do SUVAT from A to B. So we have a vertical height difference of 0 and some horizontal height difference. Thank you for the follow. Yeah, so we could take it from anywhere between point A and point B. If we threw something off a cliff and it went further downwards than we started, we could also do it down there, but anywhere along its motion, we can work it out. So the method here is split into horizontal and vertical components, and then solve SUVAT for missing. Okay, so this is our general method that we're going to be using. Is for a given problem, you split them into horizontal and vertical and then solve SUVAT. So as I said. Zooming in on our point A, that's yeeted with some initial velocity u, which is at some angle theta, okay, to the x. So if I x, okay, we're going to go back to our trig functions. So this is sort of why we're assuming a good amount of knowledge, but I'll just make sure that I go over it now so we don't need to worry about it. If a spherical cow can be modeled as a point mass, then yes. So, and the note, remember, Sakatawa. Okay, so the horizontal and vertical components of U are precisely the lengths, the sides of these triangles, right? So our if you remember your right angle triangles and you've got value theta, and then this length is U because our vectors, we draw them as lines with magnitude. We want, so we've got a hypotenuse, so we don't need that one. And then our saw, so sine is opposite and hypotenuse. So here, this value, and this is our y, and then this is our x. So these are our velocities in the horizontal and vertical directions, okay? Rather than being straight up, we're saying, what if it moved horizontally and vertically separately? They kind of add up to make you sort of average between the two. So sine theta is O over H. So sine theta is Y over U, because U is Y is opposite, and our hypotenuse is U. Hi, welcome in. This is maths. We're doing some maths. It's fun maths, I promise. And that gives us that our y component, our vertical velocity, is u sine theta. And similarly, okay, we have x is, so cos theta even, is a over h. So adjacent, which is the side next to the angle, so that's x over u. So that gives us our x component of the velocity is u cos theta. Okay. So all we're doing here is we're taking that vector u in a given direction with some angle theta, and we're saying that just how much it moves upwards, how much speed it has upwards is, or velocity it has upwards, u sine theta, and in the horizontal is u cos theta. So it's really important when you do SUVAT equations to make sure that you do this like vector decomposition into its horizontal and vertical. Otherwise, you're gonna have issues. So let's find out some stuff. So the general equation of motion for a projectile. So by this, I mean, if I have my projectile here and it's moving in this sort of direction, if I were to, ooh, dear, please, stick some axes on it, I want, what is this line as y equals f of t, okay? X, sorry. Right, so it's a function, it's gonna have an equation. So what is this? So I want an expression for y in terms of x. So because they all have the same, we're not changing anything super snazzy with it. But if we know this, maybe this will help. So remember, we've got our... this one. So we're throwing it from a given point. We have some initial value. We have our constant acceleration. We have some arbitrary time it takes us to get from point A to point B. Let's figure it out. So things we know. So we have our SUVAT. Okay, and then we need to do these in the horizontal, and we need to do them in the vertical as well. It would help if I actually wrote my U's the way I'm supposed to. Because remember, they're separate. So we don't really know much about S. Our S is our X in the horizontal, because we go some distance X across for some arbitrary number. Our U is then U cos theta. Remember, we're beating it at that angle, so there's some broken decomposition of it. V is V. A in the horizontal, so acceleration in the horizontal is 0. We don't have any of it. And T is T. Okay, so in terms of ones that we don't have in this equation, I'm going to say that one, let's get rid of. We don't know what it is, so let's just ignore it. Okay, vertical. Vertical is Y. Our distance is Y, so we want, this is what we're looking for, right? We're looking for Y in terms of X, displacement in terms of displacement. U then is U sine theta. I'm gonna disregard V again. Now our acceleration is minus gravity, minus G, and again our T is time. So time is constant in both of them, right? This is why I wanted to keep time and not velocity, final velocity, because they might be different. You might have a different speed in the horizontal and the vertical, but time to get to a point is going to be the same. So given that we've got rid of V, we go all the way back up to this wonderful little thing, and we say which is the equation that does not have final velocity in it, and it's S is ut plus half at squared. So that's the one we have to use. So horizontally, we have S is ut plus half at squared, and then we just plug in our values. So we get X is U cos theta T plus 0. Acceleration is 0, it goes away. In contrast then, the vertical equation, again, we've got no V, so let's do the same equation. So S is now ut plus half at squared. Let's plug in our values for the vertical motion. We have Y is U sine theta T plus half minus G squared. Okay, so let's do some manipulation. The plus 0 goes away. I just wrote it in case anyone wondered where that at squared went to. So this gives us that, I'm going to actually write this in terms of t so I can try and get rid of it, because remember we're trying to get y is f of x, so we want to kind of merge these two equations. We've got x in one and we've got y in one. Thank you for the follow, welcome in. So I'm going to try and get t equals something here, so that I can plug it into the other side. So dividing by u cos theta, assuming the angle isn't straight up. Yeah, otherwise it breaks. Can't divide by 0, kids. Don't do it. It's not cool. It's not funny. I'm going to get t is x over u cos theta. And then I'm going to, which we plug in that equation. Does make me query what the use of plug-in came from. Like before we had plugs. Anyway, so we have again y is u sine theta, and now where I had a t before, I'm going to put x over u cos theta. and then I've got minus g over 2. Now I have a t squared. So I have x squared over u squared cos squared theta. And then we just do some algebraic manipulation, which I tried to pretend wasn't in mechanics, but it is actually quite a lot. So we have the fact that sine over cos equals tan for the first bit. So let's do the u's cancel. We've got u on the top and we've got a u on the bottom. We get x tan theta from that first part of the equation. And then the second part, we leave the g over 2u squared or x squared to u squared alone. And then we use the fact that 1 over cos squared equals sec squared. And we use the fact that sec squared is 1 plus tan squared. 1 plus tan squared. Okay. So this gives us our equation for motion. We now have our y in terms of x. Probably analog computing machines that use y's where you literally have to plug would be my guess. I think so. I think that makes sense. Although, yeah. Unless it's like pre-computing and it was like, because you get all plugs. Why do I get distracted with etymology quite so much? Comes from Middle Dutch or Low German of unknown origin. Might come from the Norwegian, meaning wedge, which is borrowed from Low German. Why do we say we plug things into equation beyond, like, I know that we, like, to insert A into B the equation bit, but then why that? I got distracted is what happened, Tech. I'm sorry. Hello, Brian. Things are good. We're doing some maths. We're doing some mechanics. Technically, we're doing kinematics at the minute. I made an equation. Look at my nice equation. The word plug may have come from the Dutch word plugen. Sailors used the word in the 1620s. They were stopping leaks on boats. Love that. Absolutely love that. There we go. So we blame the sailors for why kinematics exists. No. There's probably some cool equations we could do with air resistance with boats and sails. But that's a future problem. We're doing kinematics at the minute. Okay, so we can figure out sort of, that gives us a general equation in terms of how to describe the arc. And fun fact, this is parabolic, right? Because you've got an x squared. The tan thetas look scary, they're just constants. So you've got an x squared minus an x minus x squared equation. It's going to be loosely parabolic, which just means it has a nice curve to it. There is some more technical definition of parabolic, but beyond it being x squared terms, don't worry. So the other cool things that we can work out as sort of general equations is, so we can also work out equations for range, max range, and max height. And here range we talk about in the horizontal direction. So what that means is if we have something like this, where we have A, now we're going to put B up here and then C, we can work out sort of this bit as H max, and then do I mean max range? No, I just mean range. There were too many things. There we go. You plug holes to stop the ship from sinking, just like you plug equations to stop your brain from melting out your ears. Melting equals leaking. That makes sense. That makes perfect sense to me. Yeah. Okay. So going back to it. So our range is essentially equivalent to what is this distance for initial points A and final point C. Okay. So SUVAT in the horizontal, we have 0 acceleration. That's by default. We have some initial velocity, but remember that it's u cos theta. Technically, we don't really care about it, nor do we know it. This is our max range, so I'm going to call it R, and then we have T. Again, we don't have V, so we're using a lot of this S is ut plus half at squared stuff, but because acceleration is 0, that instantly goes away. So we get R is cos theta t, which is great, and we could be done there, but that's not the most helpful because it's in terms of time. So let's now look vertically to see if it helps. This is now u sine theta. This is now 0, right? Because we're going from A to C, and I'm saying those two are on a flat plane. We actually have 0 displacement in the vertical. Don't care about that. Minus g there, and t. So ut plus half at squared. Hey, monkey man, how's it going? So we now have 0 is u sine theta t minus g squared, half gt squared. Whoops. So this equation now, because it's equal to 0, we can do something quite cool. So we can say that 0 is equals to t u sine theta minus half gt. Okay? So all I've done is just taken that t out. So when we have this, the only way to get so if a times b equals 0, then either a equals 0 or b equals 0. Okay? So, and this is true. Okay? If two things multiply together to get 0, or both, it's an inclusive or both. So one of those two things has to be 0. So if t was equal to 0, if no time had passed, then what would happen is A would be equal to C, and it wouldn't have gone anywhere yet. Okay? Because at when I am, I'm still there. Thank you for following after that weird soup. Appreciate it greatly. Welcome in. Yeah. So that means either t equals 0, nothing's happened, or 0 is u sine theta minus half. I actually got the doctorate being frowned. Oh yeah. Oh yeah. I just like befuddled them until they let me leave. No, I didn't. Okay, so this is now helpful. The quadratic equation in t was stressful. We've managed to get rid of one. So let's rearrange this in terms of time. And we get that, what do we get? We get u sine theta, 2u sine theta over g is equals to t. So I've just manipulated that equation, moved it around. And that is our time of flight. But if you remember, we also have this equation. So we have r is u cos theta t. From the horizontal, have that. So we can insert one into, we can plug one into the other, okay? When combining gives us R is u cos theta 2u sine theta over g. Yes. Meaning that our range is u squared over g 2 cos theta sine theta, which from trigonometries, I think is the technical term for it, that is equals to sine 2 theta from trig. There's a whole identity to go with it, but let's not worry about that for the minute. So that gives us that the range is u squared sine 2 theta over g. Okay. So that's how far away it goes. So depending on the angle, that's going to change. And that actually has maximum. Oh, there was max range. When theta is 45 degrees. Okay, which means, oh, come on. Which means in order to yeet furthest, one must throw at 45 degrees to the horizontal. Okay, lower than that and you don't get enough up to get you far. Further than that and you've got too much up and not enough forwards. So if you're going to yeet something really, really far, best angle 45, exactly halfway. Fun fact. Yeah, yeeting 45 degrees is optimal for furthest horizontal distance if you so choose. And you can think about it in terms of like, if we do this, and then I yeet something really high, it's going to have a really short arc. If I yeet it really, really low to the ground, it's going to kind of die off too quick because it doesn't have enough up. And then the nice one is going to be 45 degrees. This is an exaggeration, but 45 degrees, let's say that's closer to like 80 degrees and that's closer to like 15 degrees. Yeah, so it's that sort of, you're maximizing horizontal to vertical. And funnily enough, it's just halfway. Halfway between the two, it turns out, balances them. Who knew? So, let's talk max height. So obviously, if we wanted to maximize the height we reach, we just throw upwards. We don't lose any energy going horizontal, we just yeet up. Max possible. Yeet vertically. Okay, there's no horizontal. Okay. But if for a given projectile with angle theta, the max height reached can be calculated. And this is because the velocity at this point, so if again we go back to my questionable parabolic drawings, so it's at this point here, right? It's at the peak of the thing. It's just before it turns around and starts coming back. So this is our max height. And it has velocity 0, okay? Because its velocity, remember, is directional. So as it turns around, it has to stop before it goes back down. Yeah, I'm getting down with the Gen Z here. Gen Alpha, I don't know my internet speak. I feel like a lot of the like let's translate to Gen Z vibes is just taking a lot of like the queer culture memes that have been around for years, and then also some weird Riz thing. Okay, so let's calculate it. So we have this sort of thing happening, and B is here, A is here. Now let's SUVAT it. So horizontal SUVAT. Distance, don't really care about it. Do we even need horizontal? No, let's just do vertical. Let's just do vertical. So that means our distance is our h. That's our total height. I'm 27, I'm Gen Z, we're getting old. We are. I mean, depending on who you talk to, it's like 26-year-olds to 30-year-olds are sort of the boundary. Is who can remember rewinding a VHS tape? Seems to be the denomination between people that I enjoy the most, at the very least, because it does put me on the older end. Our initial velocity is our u sine theta. Remember, it's being thrown at an angle theta, so we need that sine theta to correct upwards. Final velocity is 0. It turns around. Acceleration is minus g, and no one cares about time. We don't need any time. So we have those three, which means we need the equation v squared is u squared plus 2as. And I could do that by going and looking at that big table that I made, but realistically I just remember it because I've got it written down in front of me. So I get to cheat. But if you wanted to, just double check in case you think I'm lying. We go all the way up here. I give you an eyesore with the non-constant scrolling, and then we check. We say no time. V squared is u squared plus 2as. Yeah. There is an easier way to do this, but this is what you get. Hey, Cat and Chat, nice to cover your channel. Congrats on your PhD. Yay, thank you. Also applied maths fluids person. Yay, welcome. More than welcome. Actively welcome. I mean, everyone else is as well, but like, you know. What do you do if you don't mind me asking? That's very cool. We love, yeah, there's a small growing group of mathematicians here. Just slowly try and pull everyone over. Okay. So our equation, stop it. Our equation is v squared is u squared plus 2as. So we have 0 on the left-hand side. Our u squared is then u squared sine squared theta times 2 times minus g h. Rearranging this, we get u squared sine squared theta over 2g equals h. Okay, and this is our h max. This is our maximum height reached. So actually, I'm just gonna do max. So that will come in handy. So this equation and the equation for range and like the maximum range with the angles, like they're not, they're not a default SUVAT equation. They are specifically projectile, and they tend to be more sort of, they'll probably come in useful. Some exam style questions might like ask you to derive them or derive the equation of motion, and then it will ask you to do something with it. Like this question we have now. So, good to do. As I say, question. I shouldn't try and talk while I'm writing. As I say, these questions were written by me, so they were inspired by exam papers, which means A, the numbers probably aren't going to be as nice as you would see in an exam style question, and B, they haven't been like tested for sufficient difficulty or like comparison to other exam questions. It's part of the does maths exam board. Yeah, exactly. Sorry, the doctor does maths board. But keep it in mind. So let's get to it. Can I write in lilac? I can. Amazing. So let's put that there. So a particle is thrown off a cliff of 5 meters upwards at an angle alpha to the horizontal with an initial velocity u meters per second. Reaches a maximum height of 8 meters before hitting a target on the ground 30 meters away. Find the angle alpha and the time the ball is in the air. Ah, boo. Nailed it. And then we just need u meters per second there. Find the angle alpha. Yeah, go team. Okay, that's the question. So we've got 2 parts to it. Find the angle and then find the time that it is in the air for. Ooh, which I haven't written the answers for, so let's figure it out. So first things first, let's do a little diagram, because everything is made better with a diagram. And I challenge you, no. Okay. Thank you for the follow. Welcome in. Let's just do not to scale to save me. So we have our point A, we have our point B, and we have our target T. Hello, welcome in. Very rectangular cliff. Yeah, it's fine. We don't need any more complicated than this. So we have that this height here is 5. We have, ooh, okay, let's get rid of that there. This height here is 8, and that's at point B. And we have that this length here is 30. If it's tricky, draw a picky. I love that so much. That's amazing. 10 out of 10. Yes, exactly that. Exactly that. And we also have some U and some alpha there. So things that will be useful in this are our equations. So V is U plus AT, S is UT plus half AT squared. VODs may end up there depending Dr. Approval. VODs may end up there depending on Cat getting internet. So at the minute we are consciously streaming off of mobile data with the awareness that it is costing me way too much to do so, but the joy that this brings and coming back to the platform is worth it. But uploading YouTube videos, I need to go elsewhere to re-upload, because I forget. But they will be there hopefully eventually. If you try and put a link, it shouts at you. I'm so sorry. I'm not getting rid of that because I don't want to get sent weird things. Do the dots and then it gets you back in. Yeah, so we're doing SUVAT. Oh, Kratos, thank you for the sub.
Just subscribed.
I appreciate it. I appreciate it. Yeah, if you tell us what the link is, I'm sure tech can give you permissions. Yes, you are welcome to whisper. I can't see them right now though. So for the data. Much appreciated. Yeah, actually check it in the Discord. We have like a really cool resources thing. If this is your videos, then I have a resource channel on my Discord that would be really cool to put it in, if that works. Yeah, so S is UT plus half AT squared, V squared is U squared plus 2AS, and S is U plus V over 2 times T. Okay. Thank you for the follow. Welcome in. And then the other one that in this case is going to be useful because we just did it, so I wrote the question that helped. Our h max is equals to u squared sine squared theta over g. 2g. We literally just did it and I've already forgotten. Yeah, u squared. So these equations are going to be helpful. And let's do our SUVAT equations. So I'm going to say that this is our origin. Okay, so A is our origin, which means that T is actually negative vertical height. So if we do from A to T, the vertical SUVAT, we have a height of or displacement of -5. We have our initial velocity again. So the other thing we need to do, which we always need to do, is gravity working downwards. Our u is our u sine theta, or sine alpha. I changed it for this equation just to mess with me. V we don't have. A is -g, and t is some time. So we don't have a v, so I'm going to use the s is ut plus half at squared. So s is ut plus half at squared in this equation. I need to just like preload a load of pages, I think. So that gives us that -5 is equals to u sine alpha t minus g over 2 squared. Over 2 squared. Okay. Let's do the horizontal then. So SUVAT. Horizontal, we have that it's 30 meters. We have u cos alpha. No one cares. This is 0, and then this is the same t. So potentially here, because we have a multiple points going on, I might actually do this as TAT. Just to show that it is, I suppose that one doesn't need it. I'm aware that says TAT, don't worry about it. But specifically, that time, that t here, is equivalent to this one. I'm about to do some t's that have, you know, from A to B. That's a different amount of time. But this is specifically the time it takes to go from A to B. So, same equation. That goes away. We have 0 acceleration. So we have 30 is u cos alpha t, at. Or more specifically, TAT is 30 over u cos alpha. Thank you, Tech. Used to be great at physics in high school, now I'm in 3rd year of med school. Congrats. I forgot most of the stuff. I mean, that's fair. It's all repetition and practice. Kirchhoff problems, don't know what those are. So you're beating me. Okay, so that gives us a value for time. So we can plug this into the equation up here. So subbing in 1. I'm just going to start labeling equations because this is about to get really messy. So this is equation 1, this is equation 2. We have that -5 is u sine alpha 30 over u cos alpha minus g over 2 30 over u cos alpha all squared. Okay. Complicated electrical circuits. Okay. Very far away from anything I know. So very cool. Okay, so that gives us that what does that give us? We have -5 is, so the u's cancel, so we get 30 tan alpha, sine over cos is tan, minus g over, so 30 squared is 900. Yeah, 900. 900 over 2. 450. Yes? I believe I'm right. This is the moment where... Yeah, okay, go me. So, my workings out here are wrong. Amazing. Thank you so much. I will definitely go check that out. Okay. So we want to get rid of that u on the bottom. So we ideally just want to get it in terms of things. So we need... get rid of squared. So AB. Okay, so remember that we have H max is that equation above. So H max is u squared sine squared over 2g. So down here, if we do the vertical SUVAT for from A to B, getting rid of you sounds so harsh. No, I'm sorry. I'm sorry. I don't mean you. I mean you. Like that one. Okay, so distance here. So our displacement, remember how I said that we were going to put A as our starting point. So our height reached is actually only 3 instead of 8. Okay, because we don't count the 5 down. What's the best textbook for classical mechanics? Taylor's or Landau and Lifshitz? Landau and Lifshitz is good. I'm a big fan of Gregory. So this one. Mostly because this is what I was taught from. But I do like... I think it has nice diagrams. I think it's explained reasonably well. I have referenced, the Landau and Lifshitz one quite regularly as well. Always ready to go to pull out a textbook as well. Okay, so yeah, let's do the vertical SUVAT. So we have, so the height is 3. Our initial velocity again is u sine of alpha. Vertical velocity at the end point is 0. Our acceleration is minus g, and we don't really care about time. But we already have the equation here, so we have h max is u squared sine squared alpha 2g. See if we remember this. U squared sine squared alpha over 2g, which means we can just plug this in. So we actually get that 6g over sine squared alpha is u squared, which we can plug in. So if this is equation 3, this is equation 4, so we plug 4 into 3. A lot of g, exactly. So we get -5 is 30 tan alpha minus g. That should be a squared there. So this is over, so we get sine squared alpha over 6g cos squared alpha times 450. So, I believe we get that the g's cancel. We get -5 is 30 tan alpha. 450 divided by 6 is a number. 75? It had a 15 feeling about it. Yeah, 75. Tan squared alpha. Okay, and this just gives us, so 75 tan squared alpha minus 30 tan alpha minus 5 equals 0. So this is just a quadratic equation. Okay, which we can solve, and we could use, let's use the minus b plus or minus square root b squared minus 4ac all over 2a for ax squared plus bx plus c equals 0. But we're not going to do that because I can't be bothered. So I'm just going to plug it into Wolfram Alpha. If you wanted to work it out yourself, you definitely can. And I pray it gives me a nice answer. What are my solutions? So we get tan alpha is a fifth minus 2 square root or plus minus 2/3 over 5. That's disgusting. So we get the alpha. One day I'll actually write an equation that is that has nice solutions. I'll write in a question that has nice solutions, but today is not that day. This is not a nice exam question. This is the sort of exam question that you get and then you're like, what on earth is that? But that gives us our angle, which is some value. So let's do arctan of 0.2 times 1 plus 2 square root 2/3. So we take the positive, because I think the negative doesn't exist, and you get that alpha is approximately 28 degrees. Which, yeah, is a bit gross. It's 27 point something 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 something. Carried down everything under the sun and the sun itself, yeah. Okay, and then finally, we do our, let's do a horizontal one of AT. So SUVAT. That's our 0. This is our 30. This is our U cos alpha, which we now know because we've worked it out. Don't care about that. And this is our question mark. So we want everything that doesn't have a V in it. So again, UT plus half AT squared. And we get that 30 is U cos alpha T. So T, again, we did this already. 30 over U cos alpha, which we can't actually work out because we don't know what U is. So I've just written that as an awful question. But cos of 28 degrees is going to be about 0.88. So T is 30 over 0.88 u to the minus 1. That's awful, I'm so sorry. Seconds. And that's an exam style question. Oh, that's really gross. I am terribly, terribly sorry. Conclusion should be that whoever threw that has a very strong arm. Yeah. Yeah. You can tell I got so far in like designing the question and then I just kind of gave up. Because I sanity checked to here and then I did this bit wrong. So I had a different answer there. Oh, it's gone into a break. It's fine. We're just chatting. This would 100% be on the physics exam. Yeah. So out of curiosity, if it was like 30 over 0.8 times 5, that's like 7.5. It's fine. Right, I have one more question and then I think we're going to call it there because this is starting to get on a bit. Never take my exams. Don't do it. Don't do it. Exam style. Question 2. Want to try it myself? By all means. Scenario for this question might also be a different planet like a nice deep. Well, gravity was actually irrelevant because I prescribed the height and the horizontal distance. So I predetermined what that parabola looked like. Which, yeah, maybe it's insane. Who knows? Okay. So, this is where I get to draw a graph. Okay. We're going to pretend that that lines up. Look at this graph. Yeah. I need to not just like read things out without thinking through the sounds that come out of my voice, but you know. Oh well. We have a car moving along a straight road with constant Okay. So essentially what this is saying is that this is just my way of making sure that I'm describing things. So you have a velocity time graph, it's passed through a point, and then these are seconds counting away from since it passed that point. So we're saying it's just moving through a point A with some velocity graph, where A is a given point. So it's got v meters per second on the vertical and t seconds along the horizontal. Your questions then become A, describe the motion of the car. B, determine acceleration of the car at equals 5 seconds. And C, the distance the car traveled is more than its displacement With evidence, do you agree? Basically. I'm not using the Pomodoro technique. Jeez. Okay, so we have 3 parts to this question. Describe the motion, determine the acceleration of the car at t equals 5, and then do we agree or disagree with the sentence, the distance the car traveled is more than twice its displacement, yes or no, and why? So this is what we have to work with. So describing this motion, we have that it's a flat v equals 6, right, for the first 4 seconds of travel. So it's moving with constant velocity in the positive direction because the velocity is positive. So it's moving forwards at constant velocity, which is of 6 meters per second for the first 4 seconds, at which point the graph then kind of tanks downwards really quickly towards 0. So as it's going towards 0, the velocity or the speed is slowing down and the velocity is actually decreasing here. So velocity increasing, decreasing is just whether or not the line is going upwards or downwards. The speed increasing and decreasing is getting close to 0. So this is where it gets mildly confusing here. So we have for part A, and I'm just going to label these 1, 2, 3, and 4. So for part A, in 1, got constant velocity of 6 meters per second. In 2, we have quick decrease velocity and 0 velocity at 6 seconds. Yeah, so as soon as that line crosses the x-axis, this is where it has 0 velocity again. Then we see it continue downwards. So now it's increasing speed because it's moving away from 0, but it's still gaining negative velocity because it's starting to move backwards, is what's happening here. We're assuming it's moving along a straight road, so it's moving backwards. So in 3, picking up speed, negative velocity for 4 seconds. Did I check my times? Yeah, 4 seconds. And then finally, it's slowing down again. Before coming back to rest. So remember, this is a velocity time graph, so even though it's slowing down, whilst the velocity itself is negative, it's still moving in that negative direction. So essentially, it looks like it's kind of constantly moving, very quickly stops, and then sort of picks up speed, and then slowly loses speed again. Spotting a parking spot, panic braking, then reversing into it. That sums it up very, very well. Yeah. Determine the acceleration of the car at t equals 5. So at t equals 5, we're at like here. So we're in that like panic braking section. So yeah, constant L panic brake, speeding up, slowing down. Okay. So to do the acceleration during that point, the acceleration is constant because the gradient is constant. So we can just do rise over run of that entire triangle. So for part B, we have this sort of thing going on. So this is 4, this is 6, this is 0, this is 6. So we have A is rise over run. So that's So rise is, we read from left to right and bottom to top. So rise is 0 to 6, so 6, yeah, 0 minus 6. No, sorry, top minus bottom and right minus left. 6 minus 4. That made sense in my head. This is the right way around. So we end up with minus 6 over 2, which is minus 3 meters per second squared. So that is quite fast deceleration. Maybe? Who knows? It's not instantaneous. C finally then is distance is more than twice the displacement. So we need to work out those two things. So we get the distance is basically just like the absolute size of these things. So it's going to be like 1 plus 2 plus 3 plus 4, where these are areas of. Okay. So panic braking, yeah. We can work these out. So this is all just rectangles and triangles, and we're just adding them together. So the total distance then, and we just need to work out these rectangles. So the first one has base times height of 6 times 4 plus 6 times 2 over 2, get the triangle, plus 6 times 4 over 2 plus 6 times 2 over 2, which gives us 24 plus 6 plus 12 plus 6, which gives us 48. Yes. So 48 meters total is how far we've traveled. Displacement then. Total time for your previous questions, square root 16 g over square root 6 over g. 2 seconds. Quite fast then. That's quite fast. So displacement is positive, you know, velocity direction is taken into account. Did you discount mass simply for doing the math? Yes, so we're looking at sort of projectiles of particles. So we basically disregard mass when we're doing this. We also disregard air resistance. Yeah, that sounds way too small. Okay, so on this question, we've got velocity in the positive direction and then velocity in the negative direction. So we need to take that value into account, whereas before I was just doing the sizes of things. So 3 and 4 are now negative areas because they're underneath the x-axis. Massless car has been compressed into a point. Exactly. So we can use the thing above, but now we're doing 1 plus 2 minus 3 minus 4 because the 3 and 4 are in the negative quadrant. So we get 24 plus 6 minus 12 minus 6, which is 12. So I think we can say with like pretty good certainty that the hence we agree with the statement as distance is actually 3 times displacement. So somehow we managed to travel 3 times the length of the distance that we moved. 5 massless people at a time. Exactly. Yeah, so that's the sort of style of time graph questions. Sometimes they're displacement time, sometimes they're velocity time. Generally speaking, you're looking at sort of straight line segments. If you're not, and you're describing curves, that also happens. The other thing that might pop up with these style of questions on kinematics, so you may also be given, so this is where you start seeing like x of t, v of t, or a of t, which is just your like position, velocity, displacement, velocity, and acceleration with respect to time, which again, you then start doing some calculus with, so you get dx dt. A is dv t, which is the second order derivative of time, displacement with respect to time, or similarly, if you get that v is the integral of a dt and x is actually the integral of v dt, which is the integral of a dt. This is bad notation, but essentially that's what happens. So you might get some questions that make you do this sort of thing, where it's given in vector form. I don't really have time to go through it today beyond this taking like 3 hours, and that's more on the calculus end of things than what I want to go through for today. But yeah, generally speaking, you've got your time graphs, you've got projectile questions. Your SUVAT equations can come in. I've seen exam questions pop up with like free fall and skydivers and that sort of thing, where you just have vertical motion. Just having horizontal motion with it is a bit boring because you just have constant velocity, and that's more where the graphs come in, because at least you can break it up into segments and it's a bit nicer. So yeah, that's where we're going to wrap things up there.